start with report outs from the breakout sessions. And we'll start with the FI. Ali Niknejad from UC Berkeley will present.
Okay, hi everyone. I'm Ali Niknejad, and thanks for Juhan for also being the scribe for the session. So we co-led the session together, and this was the FI breakout group, and we have a nice lively discussion. So we start out with highlights, and I'd just like to point out not everything, not enough room for everyone here, but just some of the things that came to fore. We heard from Austin Egbert from Baylor University on adaptive impedance tuners to be able to improve power amplifier efficiency. So actively being able to tune the impedances to different frequencies so that you can improve efficiency and not have to design a broadband system. We heard about from Mona Jarahi about taking a terahertz system, that takes up a desktop today and bringing it into a chip scale. So extreme size reduction with integration. We heard about an interesting project from Bob Jackson, UMass Amherst, about how to add security onto radar signals by adding a secondary signal onto the radar that jams the signal unless you know about it and know how to decode it. So very interesting research. We heard about tunable transmission lines with 2-to-1 tuning range and very high, to support very high dynamic range systems. 1 to 2 gigahertz band. This is from Ethan Wang, UCLA. I forgot to put his name here. Ethan pointed out that radar and communication systems are very different, and trying to build a communication system that can handle the linearity requirements of a radar system is very difficult, so you need filtering to do that. We heard from Hossein Hashemi from University of Southern California about inverse design. Basically, completely different way of designing circuits. Instead of starting out with inductors and capacitors and transistors, you start out with specifications and you say, design it for me. And this inverse design comes up with a layout of, let's say, a passive filter or an active filter that's unrecognizable by humans. It just looks like a QR code, but it actually does the filtering that you want it to do. So there's some nice applications of that for like security and privacy and things like that, being able to have your design be private and not capable of being understood by others. We heard from Ben Wu from Rowan College of Engineering about RF over photonics. RF over photonics has a lot of interesting applications. In the RF domain, you can do beamforming, you can do spatial separation of signals, you can send signals a long distance with low loss, you could use it to synchronize multiple LOs. And there's a lot of bandwidth, obviously. So if you can solve issues with how to modulate and demodulate wideband RF signals onto optical carriers, there's potentially a lot of interesting applications. Some work from my group, building more efficient millimeter wave PAs at backoff, particularly designing for better backoff efficiency using both Doherty techniques at millimeter wave frequencies, which haven't really been done before, which led us to actually using non-Doherty techniques or isolating PA techniques, which I highlighted in my poster. Also from Juhan, applications of reconfigurable holographic surfaces for 6G networks. So these were some of the highlights. Again, I apologize I didn't get everybody's highlights. But now I'll go into some of the discussions that we had, both of what are some interesting current research problems, what are some good directions to take for the future. There's a lot of interest in smart surfaces or reconfigurable intelligent surfaces, or more generally holographic surfaces, reconfigurable holographic surfaces, metamaterials, metasurfaces, lots of names, an old idea, but it's becoming more popular again. And what could you do with these surfaces? We heard from some of the talks this morning. They could be repeaters. They can have very large aperture, so you can have a lot of gain to overcome the scattering losses that you have. These are passive systems, so the power loss is like 1/r⁴, so very quickly the power goes down unless you have a very large array. So how do you make these cheaper? Can you use CMOS technology? Can you use a complete passive solution? And then there's some interesting discussion that if you make them reconfigurable and intelligent and put in all this hardware, why not just build a phased array? So there was a nice debate about do they make sense? And so that was an interesting discussion. There's also, you can also use these things to change frequency bands, right? You have an incoming signal. If it's more of an active system, you could use it to not only redirect the beam in a new direction, but you can also switch the frequency and so make it a repeater. And so you can imagine a millimeter wave solution that can't penetrate a house. Maybe you have one of these on the outside of the building that converts the signals to a lower frequency band that you could use. So there's interesting applications for it, but there's still some question marks on, how expensive are they going to be, how efficient are they going to be, and so on. But definitely a very interesting research topic. We also had some discussions about other ways of doing things, like leaky wave antennas was mentioned in one of the keynote talks today. But are they efficient enough? Are these techniques really useful once you have phased arrays? Up to upper millimeter wave bands today, we can build very cost-effective phased arrays. And so a lot of these techniques were invented in the old days when people couldn't build phased arrays. They had to resort to building kind of physics-based phased arrays. So do we need those ideas today? So that was a discussion we had. I don't want to make any conclusions here. Also, a lot of interesting research projects that we're hearing about these days are on joint communication and sensing, or I was told ESAC is what I should be calling it. So basically, I guess that's the 6G terminology for joint sensing and communication. Very interesting because, there was also a discussion about should you even be doing this, because the requirements for communication are very different from the requirements for doing radar. Radar signals are very high dynamic range, very low throughput. Communication signals completely opposite, high throughput. And so building a system that can do both is not easy. You're going to make compromises. You're going to have a system that's not good for either unless you can rethink. So if you try to build a FMCW radar today with a traditional RF front end, IQ front end that does communication, the performance is going to be terrible. It will not be able to handle all the interference, the self-interference, the reflections that you get, the bumper reflection, for instance, you get in a car, or a desktop reflection that you would get in a practical system. So you really have to rethink these systems, rethink about the waveforms, rethink about the joint communication and sensing, and trying to, there's good discussion from Hamid Jafar Khani from UC Irvine about how trying to do both at the same time just doesn't make sense. You have to pick one, but allow some outage probability for the other. So there's some interesting discussion that we heard. And then we also heard that a lot of these joint communication and sensing comes down to localization for many applications, and that can we do more than that, and can we see more research in that? Can we see more research on imaging, some security applications, seeing heart rates, people breathing, being able to tell human from non-human objects, detecting falls, all sorts of interesting potential applications that we'd like to see more research on. There's also some specific discussion about the challenges of the waveform. So for instance, OTFS uses square waves, has terrible side lobes, so it's very challenging to do as a bad delay Doppler in the delay Doppler domain, generates a lot of interference. What are some good alternatives like ODDM and other waveforms that we should be doing research on? Surprisingly, we didn't talk too much about millimeter wave. I think a lot has been said about millimeter wave. There is a lot of millimeter wave research. We know there's problems, right? 5G is not a success story. There's some question marks. Does it even make sense for doing mobile communication? And we do see industry kind of giving up on millimeter wave for the short term and saying, we'd really need to focus on these mid bands, and the FR3 bands from 7 gigahertz to 13 gigahertz are getting a lot of attention. We heard from Ericsson this morning, for instance, that that those are the bands to focus on. But I think from a research community perspective, there's still a lot of problems to solve, and there's still a lot of opportunity. The whole idea of doing joint radar and sensing makes communication and sensing makes sense when you can use these short wavelengths and you can use large densification and having, if you can make these low cost and build them and put them everywhere, then they can be very effective, and they can really complement cellular technology. But replacing cellular technology or mobile technology doesn't make sense. We also talked a little bit about the filtering problem. Hossein Hashemi brought up the problem that all communications today is really interference limited, and the solution is lots and lots of filters, right? If you open up your phone, you're going to see dozens of acoustic filters that are filtering specific bands and allowing the system to work. And what do you do as you go above 5-6 gigahertz? Acoustic filters are not there today commercially, so that's a good research problem. And fundamentally, the issue is that acoustic wave velocity is much slower than the speed of light, so you can build reasonably sized devices with lots of filtering. So it's a good research problem. How do we take this to higher frequencies? Apparently there's a DARPA program, there's a coffee, someone mentioned, looking at this issue and coming up with some good results with overmoded resonators. Finally, PA efficiency, or if you will, inefficiency, is probably a big elephant in the room. People are excited about millimeter waves. Now people are talking terahertz and sub-terahertz. But keep in mind that you need to transmit power, and you need to do so efficiently. And designing PAs is maybe not a sexy problem, but it's a real problem. Today's power amplifiers at millimeter wave frequencies have sub 10% efficiency at peak, and then you back off and you're talking a few percent. So this is a really important problem that we need to work on. Finally, I won't say much about this because this was not really the right group, but we did talk a little bit about deep learning and communication. Talked about the fact that there's not that much, there's not enough data sets out there, there's not enough to learn from, and we know it's going to play an important role in communications in the future, but the community needs to open, we need to get more data, right? And I think this is going to be discussed by others. We need people like the carriers to open up their data sets and to share them, and so that we can actually use these techniques. So that's it. Thank you very much. Any questions? There's a time for questions. Any questions or comments? All right, thanks.
Thank you, Ali, and the PHI discussion group. Next, we'll have the CIS group. Walid.
Out of the way. So our session was called the CIS session, Spectrum Capabilities, and the cue from NSF was to look at the performance and how to improve the performance of satellite radar systems, passive systems, and their coexistence with, of course, active systems and others. So we primarily will focus on what open issues we identified and what do we think are recommendations moving forward in this area. So one of the first questions we started with, okay, we want to improve performance. What does performance mean in this case? And there was a really heated discussion on the fact that when we're talking about satellite systems, radar systems, communication, and so on, there are so many metrics across these systems, and how do we really take them into account, right? Because each one of us is biased towards a certain metric, for example, outage. But maybe outage doesn't make much sense for a radar system, right? So there could be other metrics for this. So a question that emerged there was, how do we make sure that when designing those systems, we are cognizant of the metrics and needs of the other systems? And we'll get later, mention a little bit how we combine those. And of course, one metric is reliability and resilience. And we had a discussion on, existential maybe discussion on what do these mean? For example, 5G, we know reliability was a big selling point, but it didn't really work. We don't see reliability achieved in the real world. So maybe resilience became the new keyword. We can perhaps let the system let go a little bit of its performance in the hope that it can recover quickly and so on. But then there was a point that, well, some applications are critical, right? An autonomous vehicle. In that case, reliability is really the only thing we can do. So we should be able to look a little bit more about these two, like reliability when appropriate, but when we can, in the broader sense, can we use resilience? And what are the tolerable, quote unquote, disruptions? So it depends on the system. So for example, there was an anecdotal example on some passive systems where you cannot even give an inch of your spectrum because they just don't want to give up that. And the question becomes, how do we share with those systems? I mean, what would be resilience in that case? I mean, probably it doesn't even make sense. So how do we define those? And another or two kind of tied in challenges, and those were discussed in the context of IoT, really, in that, if you want to have scalable sharing with large number of devices and energy is a big constraint, how do we do that, right? And that seems an important open issue, while not maybe directly related to the satellite aspect, but still important. And the other kind of a theme that emerged out of the discussion, and I have it in the first bullet, which is really this issue of modeling the behavior of the system, or some people call it interactions between the components. How does a satellite interact with a sensor on the ground, with a ground-based station, with a 5G smartphone? So how do we understand those behavior, right? How do we kind of look at these different components and their interactions? And when you start talking systems and spectrum capabilities, well, we need to understand those, not just the metrics, but also the actual systems themselves. Of course, a common theme comes in there is dynamic prediction of interference. Especially, it seems like there are some emerging use cases, for example, satellite constellations that are dynamic, where there are parameters that are changing, and how would you predict interference in that case? So our group didn't have a lot of people on hardware, meaning physical devices, but there was at least a comment that we discussed there, is that as we start moving towards actual sharing between satellite, radar, and communication systems, should we start thinking of new hardware where they are designed from the ground up in a way to be cognizant of those other systems? So is there a need for such a hardware? And a theme that we discussed a lot, and we were trying to always get out of it and go back to the technical, but seems it's an important thing in this when we talk passive system, coexistence with passive system, is that the communication between people across those communities, right? And it seems to be still lacking. Even though I know NSF made a lot of efforts in that regard, but it seems development are still siloed. And that kind of looped back to the issue of metrics. Maybe we don't really take into account the metrics technically because we just don't know how the other community is designing that system. If we don't know, and we're not aware of their metrics and how do they design their system. So collaboration is important. So with these open issues, we had one final slide on recommendations. So what should we do in this particular community? So we need new approaches to understand and model the environment and these interactions across the systems. So one way is multi-objective, right? We cannot create perhaps one metric that works on everything, but we need to be able to accommodate for those different metrics when we are designing spectrum sharing systems. And of course, AI always comes in the discussion. I know there has been a lot of discussions on data sharing in the previous session and in this session as well. Our discussion was more along the lines, there's really two paradigms now. Either those who don't believe in AI, so we just do models, or those who believe so much in AI, we don't care about models. And it seems a middle ground is needed. There has been development on what we call model-based AI, but perhaps we need to look more at open box AI, for lack of a better term. So that was contrasting the black box nature, meaning can we have AI systems that have some sort of performance guarantees? So they're not really completely model-free in some sense and not completely relying on models. And the discussion also led to this, we were all the time saying, okay, primary is sharing with secondary and so on. But then we were like, okay, should we rethink this whole primary secondary paradigm, right? I mean, maybe we should not make those designations as opposed to saying, well, there is sharing and there are certain levels of resilience. And how does sharing work in that case? So rethinking that is important. And also there was a very common theme. I did not put it in the challenges, but it was also a challenge. All the time we were, these systems need perhaps to send feedback between them, right? And how do we create new ways to perform this cross-system feedback? And of course, heeding that in some cases we need to do real-time sharing. So feedback and overhead sharing, so there's latency coming into the picture. And I mentioned the collaboration. There's a lot of political issues in this domain. For instance, there was, again, an anecdotal example saying that many of those systems are not used to sharing, right? And I mean, they haven't done spectrum sharing ever because they didn't need to. And all of a sudden we're saying, okay, we have a cellular network that needs to use your system, so how do we mitigate those barriers? And of course that is a non-technical thing, but it's important. And we also had a group who were doing a lot of test beds, and there was an interesting discussion on the lack of test beds for public good in this space, meaning test beds where we can test specifically passive active coexistence. And there was this idea of being able to have a test bed on the move, in the sense like we can relocate it easily for the community to be able to use it. And those test beds have to be low cost, because otherwise, of course, there's no point in doing it. And an example on how we would use those test beds is to, we go back to resilience. We need to break the system, and you can only break that system in a real world test bed. And that's really what we discussed.
Thank you, Walid, and the SIS group. And finally, for the spec science, Rick Berger.
And actually not being a Google, what do we call this? Google PowerPoint. You get to see what's going on. So yeah, so I led and Francesco took the minutes, which meant any errors here were because I didn't extract the right information. I can also say right now, you'll notice the first one was 20 minutes, second one was 15 minutes. I think I'll be 5 minutes. So our synopsis. So this was what we were charged with. Is we're looking in the system science, systems spectrum engineering. How are we going to get more utility and efficiency of the electromagnetic spectrum? And by the way, that is not how do we make it better for the cellular companies? How do we make it better for the satellite companies? How do we make it better for radio astronomy? It's how do we make it better for everybody? And if you ever dealt with an FCC rulemaking, it's, how do we do this in the public interest? So the state of the art. Got a really good discussion about some new things going on in Colorado. And that there's like new technologies that are able to kind of cut through things that formerly would saturate, front-end amplifier. So there are issues when someone's looking down your throat or somebody's irraditing what you're trying to measure. We're actually coming up with new spectrum engineering, spectrum science to break through that. Some work done at Carnegie Mellon on connected autonomous vehicles. And the interesting thing there is, we keep saying, oh my goodness, unlicensed, we can't count on anything. And yet for an autonomous vehicle, they're not totally relying on it. They've got their own little exclusive space, but when you need more, how can you fairly reliably use more? And by the way, not at the expense of the incumbents, which in this case is Wi-Fi and Bluetooth. A lot of people, and especially after Walid's section here, not a surprise, a lot of breakthroughs, a lot of new science in using AI for spectrum optimization. And Manisha is hiding. A lot of work on getting real-world measurements, and not just, we should get real-world measurements, but she's gotten some breakthroughs in new research directions based on taking measurements from the real world. When we found out that the real world is not MATLAB, or is not always MATLAB. So that's where we're at. What are the things that people want to ask? We actually didn't talk much about it, but it did come up. What is spectrum science? I shouldn't have said that right as John walked in. We know what spectrum science is, that's right, yeah. But you came in just in time, because this is what should we be talking to the NSF about? And actually, based on I swear, and actually we've got a lot of people here, I did not lead the audience. This is what people said. First one, increasing the number of real-world spectrum measurements. What is really out there? And again, tying into the systems group, not just measuring what's my cellular coverage, measuring what are the out-of-band emissions hitting the passive Earth sensing? What are the emissions coming from space where there used to never be emissions coming from space? We heard earlier today, there seems to be, even amongst industry, that our current propagation models have two issues. One is we tend to have a propagation model for mobile. We have a propagation model for sensing. We have a propagation model for radio telescopes, they're not speaking the same language. And as Walid pointed out in his section, this issue of we're actually thinking that different things are important. I take that back. We know different things are important to the different communities. So how can we harmonize that? And maybe this is something that's really showing issues in the community, because you just missed Walid talking about we need to talk about hardware and we need to talk about AI. In the spectrum engineering section, we were talking about, can we get low power domain specific hardware for AI? So I'm hearing a theme there. And I believe this came from academia. Usually this comes from industry. But how do we make this work with the stuff that's out there? I mean, clearly if something's up on a satellite, we want it to last for 20, 30 years. If it's geosynchronous, if it's low Earth, we don't have to worry about that. But, the things that are higher up there, it's a long way to go plug in the USB stick to do the software upgrade. Not a new issue. The nerds typically assume that it's some terrestrial source that might have a side lobe that might hit my antenna, as opposed to a satellite that's sitting directly above you, putting radio waves down your throat. Studying out-of-band interference in radio design. The FCC went out on a limb and said, hey, as you're building radios today, you ought to consider out-of-band interference. This is, for those of you in the community, this was a bit of like the FAA radio altimeter problem, where everybody was following the rules and it broke everything. But what does that mean, to be thinking about out-of-band emissions as you build a radio today? I'm sure the radio altimeter people 40 years ago were doing their best. Oh yeah, we're doing our out-of-band stuff because there is nobody here. Nobody will ever use 4 gigahertz for anything. That's like junk space. We did talk about some human things. Actually, I'll talk about H and J. Actually, first I'll do I and then H and J. New means of radiometric detection. And you know what? I forgot. Who brought that up? Yes. Tell us about it.
It's called multipath cross-correlation radiometry. It is, I think, the first new means of radiometric detection since the Dickey radiometer. And it has the ability of rejecting gain fluctuations that are caused by strong interfering signals, gain compression.
Yep. So again, and how are we going to solve these problems that we're creating? And how are we going to solve problems that were yet to be seen? This is the kind of spectrum science that we can apply, probably to lots of bands, I would think. Yes? Yeah. And then I will go to H and J, sort of the human ones. One is bridging the digital divide. How do we make, and we heard a little bit about this morning, how do we make communications more accessible in rural communities? And how do we make it more affordable for under-adopted communities? I use the example of San Diego. I could also use the example of Arlington. You can believe there is a lot of broadband in Arlington, and there are communities in Arlington that can't afford it. So how do we, we've done a good job of making it available, but at what price? And I really didn't, this came from outside, workforce development. How do we create a pipeline of spectrum engineers, scientists, and managers? Because in fact, I believe it was, spectrum manager, that was saying, where are we going to get this workforce from? So that is all I've got. So I'm standing, you'll probably do a summary, but just a reminder, there is a welcome reception just right here, so you can do your posters just here, and welcome reception. Anyone from Viavi here? It is mostly sponsored by Viavi, which means you are allowed to partake. No federal funds are involved, so thank you all very much.
right. Thank you, everyone. Let's have a round of applause for all the leads and scribes. And thank you, everyone, for, first of all, sharing your insights and your comments during the discussion session, and for also sticking out to what I can say is the largest audience for an day-end session. So we really appreciate it for being here. So we conclude today, today's program. Tomorrow, we again have a packed schedule. We have a Spectrum Week-wide welcome and keynote in the morning. In this room, Madison, we'll also have the SpectrumX Center overview, update, and community engagement. You're welcome to attend to this. And then our PI meeting will include a joint session with the SWIFT and also SpectrumX on data sharing for spectrum sharing research panel. We'll have a fantastic list of panelists who will be joining tomorrow. Followed by lunch, you will see in your programs, we have all sorts of diverse Spectrum Week events that you're welcome to attend, followed by, again, a social event. And I want to emphasize the data sharing panel. These are our panelists from academia, industry, and government, and I look forward to discussion. Some of the topics that actually came up already, especially in terms of data sets and sharing data as well as models that will help support spectrum research. With this, I'd like to thank you all for today, and I'd like to welcome John Chapin for some conclusionary remarks. And after this, I will show the videos for the poster session that will follow. John.
Yeah, thanks. These are just concluding remarks for today, as there is still lots going on tomorrow in this meeting and for the rest of the week. So first of all, it's basically a huge thank you to all of you. You know, the workshop organizers led by John have done a really good job, but this community exists for you to work together, to sponsor your work. And I'm really thrilled that you've come together this week. I had to miss most of what was happening this afternoon, so I'm very much looking forward to the reports. We at NSF take the outcomes of these kinds of meetings very seriously and really try to base our future directions in part on what you're suggesting. So thank you for those contributions. And just to say, it's really so important that we keep the momentum going of the work on spectrum that you all are doing. SWIFT is our cross-directorate fundamental research program in this area. And we've been really thrilled with what's happened here and looking forward to lots of proposals to carry this work forward in new spectrum and beyond. I do have one small thing to raise, which is you're going to see walking around this week some people with these bright red ribbons or purplish ribbons. If you read closely, it says National Spectrum R&D Plan Author Community. So we, the nation, the government, are currently in process of writing a national spectrum research and development plan. We're having a workshop on Friday this week, but we understand that many of you are not able to stay that late to participate in that workshop. So the committee members from the federal government are here this week. You'll see us in the halls. Please grab us and talk to us about that, about what you see as important directions forward. So you can influence not just NSF stuff through what's happening here, but you can also influence the national plan that's being written this year. And we would look forward to having those informal engagements over the next couple of days. So with that, I'll hand you back over for that and say, you know, on behalf of NSF, both welcome and thank you, and look forward to the further engagements.
I'd like to thank NSF for their support, as well as Hussein, John, and Hawaii for all their support during the preparation of this workshop.